It is the third video in chapter 20 of the Crystal Clear Electronics video series, where we will discuss with Szabolcs the operation of voltage regulators and current limiting circuits. In our previous video, we demonstrated a very simple voltage regulation method, but neither the idle efficiency nor the maximum load current was high. Szabolcs, what other voltage stabilization method could be used?
For higher load currents, series power supplies should be used instead. The idea is to connect a circuit with variable resistance in series with the load. By adjusting the resistance of this element, we can control the voltage drop on it and make sure that the load gets a constant voltage. The advantage of a series voltage regulator is that the current flowing through the circuit is the same as the load current, unlike the shunt power supply from the previous episode, which used the maximum current regardless of the load. Because the current usage is lower, it results in a much higher efficiency.
Wow, that sounds good, but how would we make such a circuit? If I'm right, you will need some kind of regulation because if you change the input voltage, the circuit has to automatically change its resistance.
You're correct. One of the simplest implementations of this concept is the emitter-follower series voltage regulator. It can be seen in the figure. The variable resistor is implemented by transistor Q1. The Zener diode D1 and the resistor R1 are used to generate a low current constant voltage marked UZ. It is also called the reference voltage. The base emitter voltage of a bipolar transistor is roughly constant, about 0.6 to 0.7 volts. If the reference voltage is connected to the base of the transistor, then the reference voltage minus the base emitter voltage will appear on the load according to Kirchhoff's voltage law. Since UZ and the base emitter voltage only depend slightly on the input voltage, the voltage measured at the load will be nearly constant even with varying input voltage. Choosing the right transistor for such a circuit is not difficult. If we know the maximum current required by the load, we can calculate the required base current. To do this, the maximum load current must be divided by the minimum current gain of the transistor. This parameter can be found in the transistor datasheet as HFE.
We have a BC546BTA NPN transistor on the table in front of us. Its minimum current gain is 200.
According to the datasheet, the maximum collector current of the transistor is 100 mA. It means that the transistor base must have at least 100 mA divided by 200, which is half a milliampere of current, for the circuit to work correctly in all operating conditions. The next step is to select the resistor that will adjust the current flowing through the Zener diode and into the transistor's base. For this, the minimum voltage on the resistor is divided by the maximum current flowing through it. The voltage of the resistor is equal to the difference between the input voltage and the Zener voltage. It is at a minimal value if the input voltage is also minimal. Staying with the example of the car battery used in the previous video, the minimum input voltage should be 9 volts and the Zener voltage should be 6.2 volts as it was before. The voltage difference is therefore 2.8 volts. The current flowing through the resistor is the sum of the Zener diode current and the base current. It is worth leaving a margin in the system when sizing, because if for some reason the current flowing through the base of Q1 is not enough, the transistor will not be able to stabilize. Therefore, when calculating the resistor's current, we should be prepared for a slightly higher base current, namely K times as much. This K number should now be 2. The Zener diode also needs a current of at least 1 mA, as discussed in the previous videos. This means that the total current is 1 mA plus twice a half milliamps, so a total of 2 mA. Based on this, the required resistance value is 2.8 volts divided by 2 mA, which is 1.4 kiloohms.
Unfortunately, we don't have such a resistor value in the kit, but we can use a smaller resistor instead, say 1 kiloohm. Since a smaller resistor will allow a higher current, we will be wrong in the correct direction.
Let's see if the power supply works correctly in reality. Here's the breadboard on our desk. We have already made this circuit with the 1 kΩ series resistor, as Marci has said. Here we have a 6.2 volt Zener diode, and for the load, we are again using a 10 kΩ potentiometer. It is set to its 10 kΩ maximum resistance state. We can say that there is so little current flowing through it that the power supply is not loaded. The lab supply provides the input voltage. It is now currently at 0 volts. We also measure the voltage of the output with a voltmeter, which you can see on the laptop screen. Here's another multimeter, which I'll switch into the current measurement mode. With this, we can measure the current draw from the power supply. Now, let's first examine what happens when the voltage changes in the no-load condition. I would ask Marci to slowly increase the voltage. You will see that as the input voltage increases, the output voltage increases with it. It stabilizes around about 5.7 volts. I'll ask Marci to increase the voltage a little, to say 12 volts, that's halfway between 9 and 14 volts. That's good. We are now at 12.6 volts and we're still showing this stable voltage of 5.7 volts on the output, which is about what we expected because the breakdown voltage of the Zener diode is about 6.2 to 6.3 volts. Subtracting from that, the base emitter voltage of 0.6 to 0.7 volts gives us roughly the same value. So our stabilizer works very well. I'd like to ask Marci now how much current is drawn by our circuit when it is idle.
6.7 milliamperes.
So there is some current, but it's not a very high value. Now we're asking Marci to tell us the current values. The reason Marci is reading these currents is because this screen may not be very visible to the cameras. What I'm going to do now is increase the load, that is, decrease the value of this 10 kΩ resistor, and in the meantime, Marci will show us or indicate to us if the current changes. What do you see?
Now it's growing steadily.
Where are we now?
7.3 milliamperes.
You can see that the voltage has not changed yet.
We are currently around 9 milliamperes. And now up to 24.
You can see that the voltage is a few tens of millivolts lower. It can be explained as a result of the operation of the transistor, but it is also quite close to the unloaded voltage. So we can say that regardless of the load change, this circuit can regulate the voltage, so in this respect, it works in the same way as the Zener diode stabilizer. However, there is one very significant difference, the one Marci told us, the current. The current drawn by the circuit increases in proportion to the load current. That's very good for us, because that's why the efficiency of the circuit is much better than the parallel Zener diode voltage regulator, which draws about the same current from the input source regardless of the load current. In general, series power supplies have significantly better efficiency than the solutions discussed earlier, when the difference between the input and output voltage is not much bigger than the transistor's forward voltage.
Most of the time, we don't build these power supplies from discrete parts, but instead we choose an integrated solution.
For general purposes, one of the most obvious choices is one of the components of 78 family. These have already been mentioned in the earlier chapters of the curriculum. For example, the L78 L33 with fixed output does not require any external component other than two capacitors to produce a 3.3 volt output voltage. A schematic with the simplified internal structure of the component is shown in the figure. The dotted line shows the case of the IC. This is only a logic schematic diagram. The triangle is an operational amplifier, which we do not have time to discuss in detail now. It's enough to know that the voltage at its output equals A times the voltage difference between its two inputs. This number A varies from type to type, but it can be very high, tens of thousands, hundreds of thousands, or even more. It follows that if a very small input voltage change occurs on it, it will cause a very large output voltage change. A constant reference voltage is connected to the positive input of the operational amplifier, and the output voltage of the L78-L33 power supply IC is connected to the negative input via a voltage divider. The output of the operational amplifier is connected to the base of the series transistor. Assume that the circuit is not yet on and that the input voltage U in appears at some point. Then, the positive pin of the operational amplifier will have the reference voltage, say 1 volt, but the output of the IC will still be 0 volts, so the negative pin will also be 0 volts. It will cause the voltage at the output of the operational amplifier to start to increase, since the input voltage difference is high and positive. On the emitter of the series transistor, the output voltage of the operational amplifier minus the base emitter voltage will appear, so the voltage on the negative pin of the operational amplifier will also increase. This process will continue until the negative pin of the operational amplifier has approximately the reference voltage. In practice, the operational amplifier acts as a kind of regulator in this circuit.
I think all this theory is enough. Let's see how it can be used in practice. The breadboard in front of me already has the circuitry shown in the diagram.
That's right. The output load now consists of an LED and a series connected resistor. We're using a 7805 IC here, which means it's from the same family as I explained before, but it has a 5 volt output. To do this, we need to modify the power supply of our circuit a little compared to the previous one. For example, I'm going to remove this voltmeter from here because I want to measure the output of this stabilizer IC. So, I'm gonna put these up here. I'll lower the supply voltage to 0, like before, to start from the same position. And one more important thing is that here on the breadboard, the input power supply has to be connected to the stabilizer IC. Now Marcy's task will be as before, to start slowly increasing the voltage. In the meantime, we can see the output voltage of the stabilizer IC on the laptop screen and possibly read the current drawn from the multimeter. Okay, so start increasing the voltage. You can see that as long as we are below 5 volts, nothing happens. And then we go up. And roughly now, we're looking at a stable voltage of 5 volts. You might want to increase it a little bit to 12 volts. Now we're about 10 volts, so it's very good for us. You can see that the LED is glowing. If the voltage varies, the LED's brightness doesn't change since our output voltage is constant. Let's look at something else that might be very interesting. I would ask Marcy to start slowly reducing the voltage. And let's see how the output voltage changes in the meantime. Around 9 volts, it's still steady at 5 volts, we're at 8 volts, 7, and here please turn that potentiometer more slowly. Gradually, around 6.3 to 6.7 volts, that steady 5 volts starts to drop. It is no coincidence. In the series voltage stabilizer circuits discussed so far, a bipolar transistor played the role of a variable resistor. One drawback of this solution is that the input voltage must always be 1 to 2 volts higher than the output voltage due to the saturation voltage of the transistor and other properties of the internal circuitry. Low dropout voltage regulators, in short LDOs, provide a solution to this problem. LDOs are series voltage regulators that can provide a controlled output voltage even when the input-output voltage difference is only around 100 millivolts. LDOs are identical in structure and usage to ordinary series voltage regulators. The difference comes due to the fact that they use a FET instead of a bipolar transistor. This reduces the voltage drop and eliminates the need for a large voltage difference between the input and output. These components are slightly more expensive than their counterparts with a higher dropout voltage, So you might want to use them only if you really need the benefits they offer.
We hope you enjoyed this video. In the next one we will show you a current source. See you there. Bye!
Bye!